Mixture of expert architectures enable dramatic scaling of model parameters without slowing down training and inference speed. This is achieved by routing each token to only a sparse set of expert networks. It is a key technique powering many of today's most advanced AI models. But how does it work? A transformer is composed of multiple stack layers, alternating between attention and feedforward networks. The attention mechanisms refine each token's representation by capturing its most relevant contextual dependencies within the input sequence. Afterwards, each token passes through the feedforward network FFN independently. Because the process is identical for every token embedding, we can understand the FFN by focusing on how it operates on a single token. Before the feedforward network, there is typically a normalization layer. Imagine the token embedding as a three-dimensional vector. Without any constraints, this vector can become arbitrarily large, making the training unstable. A common normalization layer addresses this instability by rescaling the vector so that they have unit norm. But constraining the norm of the vector can be overly restrictive. To address this, we assign a learnable scaling factor to each dimension. This allows the model to flexibly learn and adapt the scaling for each dimension independently. This method is known as looming square layer normalization, or RMS norm. Now let's try to understand the role of the feedforward network. Let's say we have a sequence of tokens. The capital of Taiwan is. Here, we hope the model can complete the sentence correctly. The attention mechanism helps capture the dependencies between tokens. It certainly helps the model to make sense of the contextual cues. But to accurately answer this question, having context is not enough. The model must somehow retrieve factual information embedded within its weights. This is where feedforward networks come in. Let's take the embedding vector of the last token as an example. This token embedding should already capture the relevant information about the sentence. The feedforward networks consist of three steps. First, we pass the input vector through a linear layer. This linear layer uses a learn weight matrix and a bias vector. It takes the input vector and computes a weighted sum for each hidden feature dimension. Typically, the hidden feature dimension is chosen to be 4 times larger than the size of the input vector. As a result, we represent this linear layer with an up projection matrix, denoted as W up. Let's call this feature vector Z. We compute each dimension of the vector Z by applying a dot product between the learn weight vector W and the input token embedding, followed by adding a scalar bias. Each dimension of this linear layer can be interpreted as posing a distinct question to the token. Specifically, each row in the weight matrix can be thought of as representing a semantic concept. The dot product indicates how well the input embedding vector matches each of these learned semantic directions. In our example, the first question will likely have a positive value since the question is highly relevant to the input token. The others may be close to zeros or even negative. The second part of the feedforward network is applying a nonlinear activation function for each dimension. For simplicity, suppose we use rectified linear unit as an example. This effectively removes all the irrelevant questions from the first linear layer. We denote the vector after activation as A. The third part of the feedforward network is another linear layer that maps the vector A back to the same dimensionality of the input token embedding. Since this linear layer typically reduces the dimensionality back to D, we refer this as a down projection matrix, W down. The output vector Y is formed by taking a weighted sum of the columns in the down projection matrix, using the values from the vector A as the weights. One way to interpret this down projection matrix is that its column vectors encode factual information related to specific questions posed by the first linear layer. For example, the first column vector v1 may encode the semantic concept of Taipei City. It may also consist of related concepts like TSMC or bubble tea. We then add the output vector y back into the original token embedding through the residual connection. By doing so, the model not only retains the contextual understanding from the earlier layers, but also incorporates new factual or semantic information retrieved through the feedforward network. Of course, the actual process may be much more complicated than our simple example. But this example illustrates a potential mechanism by which a feedforward network can store and retrieve factual knowledge. With this understanding, a natural approach to improve a model's capability is to increase the hidden dimension of the feedforward network. Intuitively, increasing the hidden feature dimension allows the model to ask a broader range of subtle questions and capture more fine-grained factual knowledge. But this causes two problems. It slows down both training and inference speed, and also demands more memory usage. How do we address this? For a given token, it is often unnecessary to activate all the hidden units in the network. As shown in the previous example, many of the questions and the associated factual knowledge are not relevant at all to a specific token. We can reduce the computation and memory costs by skipping these irrelevant operations. This is the core idea of sparse mixture of experts, or MoE. In a sense, we partition a large feedforward network into several smaller, more specialized expert networks. For each token, we activate only a sparse subset of expert networks to process the token. Consequently, we create a much larger and more expressive network without incurring additional computational costs and memory usage at the test time. This is great. But how do we determine which experts to activate? Here is a simple approach. Given an input token embedding, we train a router to predict one score for each expert. In our example, this results in a vector of A numbers. We then apply a softmax function to these scores and produce a probability distribution over the experts. We select the top two experts with the highest probabilities. Next, we send the input token embedding to the selected experts for processing. Each expert produces its own output. We then compute a weighted average of these outputs using the probabilities predicted from the router. This gives us the final output of the MoE layer. The routing process operates at the token level in every MoE layer of a transformer. Let's express this more explicitly. For the ith expert, we denote the logic produced by the router for input x as h of x, and the normalized probability after applying the softmax as p of x. The output vector y is computed as a weighted sum of the outputs from the selected experts, where the weights are given by the router probabilities. Since we only have the top k experts, the weights do not need to sum up to 1. This is nice. But how exactly do we implement this router? It's actually simpler than you think. The router module has learnable weight vectors G1, G2 to G8, one for each expert. We compute the logic using vector dot product between the input vector x and the weight vector g. You can think of these weight vectors are distributed in the space of token embeddings. For a given embedding vector x, we get the score for each expert by computing the dot product. Here is another example. But here we only have 8 experts to choose from. Each expert is still a fairly large feedforward network. Recent work has found that scaling up the number of experts can lead to better performance. For example, DeepSea V3's model has up to 256 small expert models. For each token, it only activates 8 of the selected feedforward networks. This critical design is called fine-grained experts. The fine-grained experts is later adopted in many of the open-source models like Crans 3 or Kimi K2. In the OL MoE paper, they perform control experiments to highlight key design choices. The results shows a clear advantage of using fine-grained experts. Another interesting design is the inclusion of a shared expert that is always active, as highlighted in the yellow box. The inclusion of a shared expert ensures that every token has access to both general-purpose expert and specialized experts at the same time. This design encourages the shared expert to learn broad, common information that benefits all inputs, while allowing the routed specialist to focus on learning more specific or nuanced patterns. But the experimental results are somewhat mixed. Contradicting to DeepSeek's results, the OL MoE's experiments do not show improvements when using a shared expert. They attribute the potential reason to the fact that converting one of the routed experts into a shared expert dramatically reduces the number of possible expert combinations. Routing with top K selections allows each input tokens to be processed by a small subset of experts, enabling both specializations and efficiency. But how do we assign input tokens to experts? The mixture of expert provides a natural way to partition the model weights across multiple devices. Each device has a specific capacity on how many tokens they can process at the same time. Here is an example. Imagine we have 16 tokens here. Based on the router, each token is routed to the best expert with the highest router probability. We can calculate the expert capacity as the total tokens in a batch divided by the number of experts. When we set the capacity vector as 1, the expert capacity is 2. This means that an expert can process 2 tokens at a time. But there's a problem. The routing is dynamic depending on the input tokens. As a result, we may not get routing decisions that are perfectly balanced across experts. In this case, we have token overflow and have to drop the tokens. This may sound concerning, but in practice, the computation of these tokens is simply skipped, and their representations are forwarded unchanged to the next level via the residual connection. One way to address this is to increase expert capacity by increasing the capacity factor. For example, now each expert can process 3 tokens at a time. However, while increasing capacity factor helps reduce token overflow, it also leads to higher computation and communication costs. Notice how these empty slots results in unnecessary computation and memory usage. But is there a way to avoid this trade-off? That is, avoid choosing between dropping tokens due to overflow or wasting computation or memory on padding. Here is one idea. Let's illustrate this with 3 experts. Here we have a batch of 9 tokens. Each token selects the most suitable experts to process it. Let's label this input embedding as x1, x2 to x9. Together, this forms a 3 by D matrix. The mixture of expert implementations we have earlier leverage batch matrix multiplications to compute all experts within a layer in parallel. Specifically, the first layer of the expert is an up projection matrix. The up projection matrices have dimensions d by dh, where dh is the hidden feature dimension. This gives us the vector z with dh dimensions. Applying the activation function to the z vectors yields the a vectors. Finally, we have the down projection matrix that maps the dh dimension vectors back to d dimension. Let's focus on the computation of the first matrix multiplication. the batch matrix multiplications allows parallel processing. But this approach imposes the constraint that all experts must be assigned to the same number of tokens. As a result, this leads to a trade-off between token overflow or wasting computation or memory on padding. The key idea here is to express the expert computation using block diagonal matrix products with equal size blocks along the diagonal. These are the dimensionalities of these block matrices. Here the gray blocks are zero vectors or zero matrices. In practice, we don't need to materialize these zero vectors and zero matrices, and instead compute this with block-sparse matrix multiplication kernel. We can get the corresponding output vectors with a block compression step that removes zeros. The benefit of this expression is that we don't need to drop tokens when the experts receive uneven number of tokens. The matrix multiplication structures remains the same as block row matrix multiplied by a block diagonal matrix. With uneven routing, the only difference is that the size of each block may vary. That is, how many tokens are routed to a given expert. This approach enables the training of a dropless MoE, removing the need to compromise between dropping tokens and wasting computation or memory. Now we understand how tokens are routed to experts and how experts process them. But how do we actually train these experts? At the start of the training, all the weights in these feedforward networks are initialized randomly. This means that all these expert networks are equally bad. Now suppose the router assigned the first few tokens to the first two experts. As these two experts are updated more frequently than others, they start to perform better. This creates a self-reinforcing behavior where the router becomes increasingly inclined to route most tokens to the first two experts. Over the course of training, the remaining experts may rarely, if ever, be activated, causing them to become effectively dead. This brings us to the load balancing problem. In other words, our goal is to distribute the processing of tokens as evenly as possible among the experts. One simple idea is to add Gaussian noise to the logics. This encourages the router to select a more diverse set of experts and prevents the same experts from always being chosen. We can further improve this by adding a tunable scaling factor for each expert. This is called noisy top K gating. The noise term helps with load balancing. But this is not enough. The router often converges to a state in which it consistently assigns large router probabilities to the same few experts. To address this problem, we can add soft constraints. For instance, the importance of each expert can be quantified by summing the router probabilities assigned to it over the entire batch. Here is an example of the importance score for a batch of 10 tokens. To encourage a more balanced probability distributions across experts, our goal is to make the importance scores as uniform as possible. One way to do this is to compute the coefficient of variations, CV. This quantifies the variability in expert importance by calculating the ratio of their standard deviation to their mean. One example here has a coefficient of variation of 1.22. When the expert importances are distributed more evenly, the CV value is lower. When the expert importances are perfectly uniform, the coefficient of variations becomes 0. This looks great. But expert importance is only a proxy for estimating load balance. Considering the following counterexample. Here we have A experts. Assume that the router assigned probabilities of 0.25 to 2 of the first 4 experts and 0.125 evenly to the remaining 4 experts. If we calculate the importance of each expert by summing up their router probabilities assigned to them, the resulting expert importance are perfectly uniform across all experts. As a result, the coefficient of variation matrix indicates zero loss in this scenario. But if we count the total number of the tokens assigned to each expert, we see a very different story. Each of the first 4 experts receive 5 tokens. The remaining 4 experts receive 0 tokens. This means that they were never activated and updated for this batch of tokens. To better encourage the experts to receive roughly equal number of training examples, we measure the load of each expert directly. This matrix explicitly counts the number of tokens that get routed to a specific expert. Unfortunately, the number of tokens received by each expert is a discrete quantity. This suggests that we cannot use this directly for backpropagation. Instead, we can define a smooth estimator for the number of examples assigned to each expert in a batch. Here, this represents the probability that expert I is selected. The smoothness enables gradients to flow through the estimator, making it possible to apply backpropagation. In summary, the load balancing loss combines the squared coefficient of variations for both importance and load. But can we simplify the computation of this load balancing loss? First, we compute the fraction of tokens assigned to expert I. Second, we compute the fraction of router probabilities allocated for expert I. We can combine these 2 measurements together as a single load balancing loss. As we mentioned previously, the fraction of tokens assigned to each expert is a discrete, non-differentiable quantity. Therefore, we cannot apply backpropagation through this. But we can use this quantity to weigh the average token importance Pi. This loss is differentiable with respect to Pi and can be easily integrated into training. The load balancing auxiliary loss encourages both fractions of tokens assigned to each expert and the average router probability per expert to approach 1/n, promoting equal expert usage and balanced token distributions. Here, alpha serves as a hyperparameter that controls the inference of the load balancing loss during training. If alpha is set too high, the load balancing loss can dominate the overall objective, potentially hindering the primary task. Conversely, if the alpha is too low, the effect on load balancing becomes negligible. But why is there a scalar n, the number of experts, here? When both Fi and Pi are uniformly distributed, this term becomes 1/n. Multiplying by a scalar n ensures that the minimum value of this term is always 1. Without that, when we increase the number of experts, the loss automatically shrinks. That will make the regularization strength depend on model size and difficult to tune. From the experimental results, we see a clear advantage of using load balancing loss. It produces lower training and validation loss. On the left-hand side, we observe that without load balancing, 2 out of 8 experts receive all the training tokens. This means that the remaining 6 experts are poorly trained. With load balancing loss, the tokens are distributed much more evenly across all experts. Excellent! But these experts may live in different devices. Therefore, in addition to expert-level balance, we can further distribute the computational load evenly across devices and alleviate bottlenecks. The computation of device-level balance loss follows a similar formulation, but aggregates the token counts and router probabilities at the device level. However, adding these losses introduces a trade-off between model performance and load balance. DeepSeek V3 used a simple trick to balance the load. Instead of using softmax, the router in DeepSeek V3 directly applied a sigmoid function on the predicted logics, one for each expert. Suppose this router is slightly biased towards selecting the first two experts. For example, in a batch of 20 tokens, it is unsurprising that the first two experts receive significantly more tokens than the others. To overcome this imbalance, we add a small bias to each expert, depending on whether the number of tokens routed to the expert is larger or smaller than the average. This gives us adjusted scores to determine top K routing. Let's try another batch of tokens. This simple bias adjustments increases the likelihood of tokens being routed to a broader range of experts. However, the first two experts still dominate the routing assignments. Let's update the bias term for each expert. By dynamically adjusting the bias for overloaded or underloaded experts, we keep balanced expert load while achieving better performance. Note that the bias adjustments was only used for determining the top K routing. The final output still uses the original probability as weights for combining expert output. Here are the results. It demonstrates that this auxiliary loss-free load balancing strategy avoids the trade-off between load balance and model performance. But it's not rainbows and unicorns. While DeepSeek v3 mainly use these strategies for load balancing, they still have to use a sequence-wise balance loss to prevent severe imbalance within individual sequences. Effective load balancing techniques for distributing tokens and computational workloads evenly across experts and devices is crucial for successfully training a mixture of expert models. But another challenge arises when scaling up the training: stability. Let's revisit the simple router design as an example. Given an input token embedding X, we use a linear projection layer to compute the logic for each expert. We then apply a softmax function on these logics to compute the router probability. The router probabilities are then used to determine the top K routing and combine the expert outputs. But when we add a constant value to all the expert logics, it does not change the softmax probabilities. Why is that the case? Here is the equation for the softmax function. First, we exponentiate each logic, and then we normalize these values by dividing by their sum, ensuring the probabilities add up to 1. Now let's see what happens when we add a scalar value c to each logic. Because the c appears in the exponent, we can factor it out for both the numerator and denominator. The two terms therefore cancel out. This suggests that the softmax is shift invariant. But this is a problem. Although the router probabilities remain unchanged, the underlying logics can grow without bound. This unbounded growth of logics becomes particularly problematic when using half-precision floating point numbers, float16, which are commonly used to speed up training and reduce memory usage. When the router logics keep increasing due to certain optimization dynamics, they could easily overflow the representable range of numbers and cause training to fail. A common strategy to address this is to use safe softmax. Safe softmax prevents overflow by first subtracting the maximal logics from all logics before exponentiating. Subtracting the max logic doesn't change softmax output, but prevents overflow from large exponentials in low positions. However, this approach only treats the symptom. It does not resolve the underlying cause. The expert logics may still grow without control and lead to numerical instability. Using safe softmax is like wearing a seatbelt while driving. It does provide important protections, but it does not mean we should press the accelerator recklessly and allow the logics to grow without constraint. So how do we regularize the logics to ensure training stability? To prevent the logics from becoming excessively large, a straightforward approach is to add a loss term that penalizes the sum of their square values. Unfortunately, this hurts the model performance because it interferes with the router probability from the softmax. What we could do instead is to penalize this normalization term. This ensures that the gradient from this loss do not change the router probabilities. But directly minimizing this loss is tricky. This is because the loss grows exponentially, which may lead to exploding gradients. Therefore, we take the logarithm of this normalization term. This helps penalize the unnecessary constant shifts and keeps logics in a numerically safe range. We square the log normalizer to penalize both positive and negative shifts and average them across the batch. This is known as the router z-loss. The router z-loss keeps the logic centered and prevents them from drifting to arbitrarily large values. Ensuring training stability is crucial for reliable scaling mixture of experts to a larger and more powerful models. Here is the controlled experiment from OL and MoE. In the orange curve, we observe that without z-loss, the training curve has many loss spikes. In contrast, adding router z-loss leads to more stable training and better performance. The router z-loss, together with the low balancing loss, are the two important design choices for the state-of-the-art mixture of expert models. The training involves the standard cross-entropy loss for next token prediction and these two regularization losses. I hope you enjoyed this overview on mixture of experts. Thanks for watching, and I will see you next time.